Today, we're going to talk about data reduction, which is an important part of data preprocessing. Here, the idea is to reduce the dimension of a data set in order to make data analysis and interpretation easier. Let's recall the terminology that we had. We talked about a data set in the form of a matrix. The rows of this matrix would be individual observations or data instances or samples. For example, this could be individual number one, individual number two, individual number three, and so on. The columns are features, predictors, or dimensions associated with each observation. For example, this would be individual number one, and these columns could represent that individual's age, height, weight, employment status, education, and so on. Each of those would be a dimension or a feature. So our goal here is to see what are the ways to reduce the dimension of that data set X. A simple technique is known as feature removal. Here we remove the features or dimensions that we consider to have little or no information associated with them. One example would be attributes or features that are very correlated. If you have high correlation between those attributes, essentially they provide redundant information. So one of them can be kept, the remaining ones can be removed from the data. Another example would be attributes that have little variability. One argument is that these attributes may not have a lot of information in them. Consider this example. This is a three-dimensional data set where you have certain amount of variability along axis 1, axis 2, and axis 3. As you can see, variability along axis 3 here is pretty limited. You can kind of assume that most of the data instances have more or less the same value or close values when it comes to dimension 3 or axis 3. In that situation, what we can do is we can remove that dimension number 3 and map this three-dimensional data set into a two-dimensional data set as I'm showing here. Mathematically speaking, it's kind of like removing one of the columns that is associated with that predictor with a very low variability. For example, you remove this column and you're taking out one dimension off of your data set. We also have more advanced approaches generally known as dimensionality reduction, and one of the most common techniques in this category is principal component analysis. Here, the idea is that we look for dimensions in the data set that have the highest variability, but these dimensions do not necessarily align with the original dimensions as I showed you on the previous slide. On the previous slide, I kept two of the original dimensions, dimension number 1 and dimension number 2, and then removed dimension number 3. Here, I look for dimensions that could in fact be linear combinations of the original dimensions. Take a look at this diagram. Imagine this is a two-dimensional data set that I have, and I have original dimension number 1, original dimension number 2. This is the amount of variability that I have along dimension number 1, and this is along dimension number 2. But if I look at my scatter plot of data points, I can see that this particular dimension is a dimension in which I have maximum variation. So I could argue that this dimension has the most amount of information associated with this data set. So I could, in fact, reduce this data set from the two original dimensions to this new dimension, which has maximum variation. These dimensions are known as principal components, and these are linear combinations of the original dimensions of the data set. And in the most general case, they do not overlap with the original dimensions. Think of principal components as kind of low-dimensional linear surfaces that you map to your original data. For example, your first principal component could be the line that you map to the data. The first two principal components could be the two-dimensional plane that you map onto your high-dimensional data set, and so on. Mathematically speaking, again, you have your data set. Remember that each row would be a data instance or a sample or an observation, and each column would be a predictor or dimension or attribute. These are the words that I use interchangeably. So in this case, I have a p-dimensional data set, capital P here. So I have dimensions x1, x2, all the way to xp. What I'm going to do is I'm going to be converting it to a lower dimensional data set, has the same number of rows, meaning that the number of data instances has not changed, but the number of dimensions changes from x1 to xp to z1 to zm, where capital M is smaller than capital P, meaning that in the new data set, I have reduced number of dimensions. One thing that I'd like you to pay attention to, as opposed to what I showed you on feature removal, here I change things from a domain of X values to a domain of Z values. So each of the new dimensions are going to be linear combinations of the X's, not the original values. Now, how do we derive those principal components? If you think about it, in my new low-dimensional data set, every new dimension, which I'm going to use an index of m to indicate it, is a linear combination of the original p dimensions or features. So I had original features x1, x2 to xp. My, let's say, new dimension number m, Zm, is going to be a linear combination of those original dimensions. You notice that I have these alpha coefficients. I show them as alpha of M1, M2, and so on. These are known as the loading coefficients, and they indicate the strength of each of the original dimensions in the new dimension M. So for example, this indicates alpha M1 indicates the strength of original dimension X1 in the new dimension ZM. Alpha M2 indicates the strength of original dimension x2 in the new dimension m, and so on. Generally, what we do is we constrain those loading coefficients to be normalized, which is their L2 norm has to be 1. Now, to find principal components, we can formulate the problem as a mathematical optimization one. Let's say I want to find the first principal component. I want to call it Z1. This is a linear combination of all the original dimensions and has the highest variability, the highest variance. Now, imagine each of my original dimensions x of p, they have a mean of 0. So the expected value of x of p is 0. This, of course, is a trivial assumption because if the mean is not 0, what I can do is I can subtract the mean from every value, and the resultant values are going to have a mean of 0. With that assumption, now for each of the observations, I can say observation number I along the new dimension 1 is going to be a loading coefficient alpha 1, 1 times observation number I along the original dimension number 1 plus, again, another coefficient alpha 1, 2, observation I along the second original dimension, and so on, all the way up to dimension P. Again, alpha 1 P's in this case would be the loading coefficients that map these original dimensions x1 through xp onto the first principal component, z1. What we want to do is we want to make sure that Z1 has the maximum variability. So mathematically, the problem is a maximization problem. You want to maximize the variance of that dimension for all the data instances. So 1 over n summation of all the Z I1s when I goes from 1 to n, from observation or data instance 1 all the way to data instance n. Keep in mind, of course, that ZI1 itself is a linear combination of all the original dimension, so I replace it with that summation. So I want to maximize that, nested summation subject to the fact that coefficients are going to be normalized. So the sum of the coefficients, loading coefficient squared, would be 1. We solve this, and the variables of this optimization would be the alpha coefficients. Once we find those coefficients, we can find the essentially mapping or projection of every observation from x1 to xn onto the first principal component direction, z1. Now that we found z1, we want to go ahead and find the second principal component. We're going to have to do the same thing. Again, we're going to have to find the direction along which we have maximum variability. However, we want to make sure that these principal components are linearly independent. In order for them to be linearly independent, the loading coefficients alpha 1p's associated with principal component z1 multiplied by loading coefficients alpha 2p's associated with principal component z2, the sum of those multiplications over all the p-values would have to be 0. That's essentially our way of saying that vector of z1 would be orthogonal to vector of z2 or linearly independent. This is important to remember that while the original dimensions 1 through p or x1 through xp may not be linearly independent and may have some level of correlation between them, the same is not does not hold for principal components. Principal components have no correlation and are linearly independent. So we do this for Z2, and as you can imagine, the process continues. So if you want to find Z3, you would find the dimension along which you have maximum variability, subject to the constraints that this new dimension is orthogonal to dimension of Z1 and orthogonal to dimension of Z2. Now, one question that you might ask is how many of these principal components do we need? I parametrically showed you in one of the previous slides that I have p original dimensions and I want to reduce the number of dimensions to some value m, which is less than p. But how much less than p? What should be that number? Do I need 3 principal components, 10 principal components? How should I find that number m? In order to do that, we have to look into the total variance of the data set that is explained using those principal components. Um, First question, what is the total variance in the data set? Obviously, would be the sum of all the xips squared, summed over all the observations from 1 to n, and all the features or predictors or attributes or dimensions from 1 to p. So that's the total variance in the data set. Then the question would be how much of the variance is explained, or how much of this total variance is explained by principal component number m. Again, the variance explained by principal component number m would be 1 over n summation of zims squared when I goes from 1 to n. Keep in mind that n is the total number of data points or observations. Instead of ZIM, I can replace it with that equation because it's a linear combination of all the original xi's. So now if I divide this term, by the total variance, I will get the proportion of the total variance that is explained by principal component number m. So I can determine how much of the total variance in the dataset is explained by principal component number 1, number 2, number 3, and so on. Then what I do is I plot the proportion of variance explained by each of those principal components. And essentially, I look for a point where that proportion of variance explained drops off significantly. Consider this case. You have this much of variance of the data set that is explained by principal component number 2. This much of it is explained by principal component number 2 and number three, and all of a sudden there's not much of a difference between number three and number four. So it seems like the amount of variance that is explained by the remaining principal components is not significant. So in this case, you could, for example, just pick the first three principal components, and that could be, majority of variance in the data set. A better way to look at it would be to kind of plot the cumulative PVE, or proportion of variance explained. Notice that if I include principal component one, I can explain this much of variance in the data set. One and two together explain this much. One, two, three together explain this much. When I add also four, the amount of variance explained goes from this value to a slightly higher value. That basically tells you that you're not gaining much by including principal component number four. So in this hypothetical example, just choosing three principal components would be sufficient. Let's take a look at an example. This is an example that I have adopted from the book, An Introduction to Statistical Learning by James and Witten. Here they worked with a data set that consisted of the number of arrests for assault, murder, and rape for each of the states in the US, as well as the urban population of that state. So essentially, this was a four-dimensional data set. That's the original data set. And they have a total number of 50 observations. What they did was they standardized each of those values first so that they are more comparable. Then they performed PCA. And then they looked at the first two principal components. So from a four-dimensional data set, they went to a two-dimensional data set. These are the loading coefficients that they had. And it was interesting because notice, for instance, that for principal component one, you can see that murder, assault, and rape, both of all three of them have kind of the same loading coefficient, but then the loading coefficient for urban population is pretty low. And then for Z2, on the other hand, murder, assault, and rape do not have a very high loading coefficient, but urban population has a high loading coefficient. So you could kind of think of it as principal component number one, kind of representing overall crime in that state, which is kind of a function of murder, assault, and rape. Whereas principal component number two represent urbanization level. I have to remind you, of course, this is a very specific example in which principal components have kind of a meaningful connotation to them. In a lot of situations, you're not going to be fortunate enough to be able to kind of figure out that type of connotation or meaning. So in a lot of practical situations, principal components are just simply going to be linear combinations of the original dimensions, and you're not going to be able to necessarily interpret them in a very nice way that they have shown in this example. What they did, again, this diagram, I have got it from that reference. They plotted these vectors for murder, assault, and rape based on those coefficients that I showed in the previous slide, as well as urban population. One thing you see is that within this reduced dimension data set, which is two-dimensional now, rape and assault and murder are kind of in the same direction, which shows that those three original dimensions had high correlation with one another. But as you can see, urban population is not very correlated with those quantities. So that's, again, another indication that it made sense to have one dimension Z1 representing crime and then another dimension representing urban population. Now, I showed you how you can find principal components through solving optimization models iteratively, first for principal component number one, and then for Z2 and Z3 and so on. That might look to you like a little bit of a tedious work, and it kind of is. The good news for us, however, is using linear algebra, we can actually simplify the process of PCA significantly. In fact, it can be shown that principal components are essentially eigenvectors of the covariance matrix of data, and the amount of variance that is explained by each one is the corresponding eigenvalues. So what we do in order to implement PCA is we first form the covariance matrix of the data, then we find its eigenvalues and sort them from the largest to the smallest, um, and essentially determine how many of these eigenvalues do we need in order to explain majority of the variability in data. As a rule of thumb, remember that we typically go for 85 to 90% of variability in data. So when we normalize these eigenvalues, we pick a number of top eigenvalues that some of them would, add up to like, 85% or 90%. That's typically our threshold. And then once we find those eigenvalues, what we do is we derive the eigenvectors associated with each one, and then by multiplying the original data instance by, let's say, eigenvector m associated with principal component number m, we can find the ZIM value. And we can repeat this for each of the new reduced dimensions. In this analysis, notice that xi in my notation is a row vector and q of m is a column vector of the same dimension. So basically multiplication of a row vector and a column vector would give you a scalar, which would be ZIM, essentially the score of observation number I along principal component number M. Before we stop this discussion, I want to make sure I go through a few practical considerations when it comes to PCA. First, remember that PCA is sensitive to skewness in data. So if your data is skewed, you're going to have to remove that skewness using techniques like Box and Cox, for example, before you apply PCA. PCA is also sensitive to scaling. This is because it looks at the variability of the data along different dimensions. And if you have original dimensions that have very, very large values compared to some other dimensions, those large values have the tendency to dominate the variability. Because of that, we typically, before applying PCA, we normalize all the features. So everything is between 0 and 1 or between -1 and 1, and then we apply PCA. This way, we make sure that none of the original dimensions dominate others. The last, but perhaps the most important point in this discussion is that PCA or feature removal that I mentioned in the beginning of this presentation, these are unsupervised approaches. What that means is that they simply assume that high variability means more relevance to the model that you have in mind. This may or may not be true. PCA, because it is unsupervised, it doesn't know the impact of variation on the output of the model that you have in mind. Let me give you an example. Imagine you have a model that has very low variability, for example, in terms of education level. Let's say majority of data instances that you have in your data set have a graduate degree. So most of them belong to the same level of education. If you feed this to PCA, the first thing that it will do is most likely it will remove that dimension of education level from the data set, from the principal components, because it assumes that it does not have a lot of variability, so should not have a lot of information, should not be very informative for the model, if you will. However, if your model at the end happens to be actually very dependent on education level, that original dimension education, despite the fact that it had low variability, would be very informative for the model. This is something that PCA does not know. PCA removes dimensions that have low variability without knowing or considering how much of an impact those dimensions might have on the output of the model that you have in mind. This is what I mean by saying that PCA is unsupervised. So this was a kind of a quick overview on data reduction techniques, which is a uh, part of data preprocessing, and hopefully gave you a better understanding of how we can take a high dimensional data set and convert it to a lower dimensional data set in order to make model development and model interpretability easier.